through the chapter 26 review guide. I want to try to just kind of do this all at once. If you really want to kind of go through this, make sure that you've either done the review guide or you can do it with me. I'm going to have my calculator out just in case, because it's going to need that. So if you haven't done it, definitely get your calculator, get your review guide out, and we can kind of walk through this. Okay, in order to do the chi-squared test at the beginning, number one, I'm going to have to use my lists. Okay, this is a goodness of fit test. So a lot of you are having questions about how to do goodness of fit. The reason I know it's goodness of fit is because, number one, I just have one set of numbers, right? You've got them right here. And so if I kind of write this out, it's going to be L1, that's going to be 226, 764, 733, and then 2277. My L2 is the thing that I don't have. So 226, 764, and 733, and 2277. The deal is, I need to know what the ratio is, right? And that's the key right here. Here's how you do the ratio. This is like number 9 on from the book. So it's x plus 3x plus 3x plus 9x equals the total sample of 4,000. That's going to give me 16 equals 16x equals 4. Is it 4,000? Is that what the number is? Yes, 4,000. So we're going to divide by 16. So we'll say, and this is going to be the just x. So this is the 1 value. So 4,000 divided by 16 equals 250. So x equals 250. So the 3x is going to be 3 times 250. That's going to be 750. And of course 9x is 9 times 250. That's your 2250. And so these are the values that I'm going to be plugging into L2. So I need 250. The next one's going to be, 750, 750. And then 2250. And so now I can run into my calculator. I can enter the actual expected values, 250. And sometimes you get decimal values for these. This was kind of nice because they gave it to me in whole number values. So I typed it in 750, then 2250 for my final one. Now I'm going to go back to stat. I'm going to go over to my goodness of fit test. I'm going to make sure that it's L1 and L2. Now I have 4 numbers in my list right here. Right, you got 4 here. That means that I'm going to have a degree of freedom of 1 less the number of values we have in our lists right here. So I have degree of freedom of 3. Just double check it. Most of the time the calculator automatically fixes that, but sometimes it's not always that way. I'm going to do this. We get a p-value of 0.35. And so we in any respectful test, we know a p-value of 0.35, we would fail to reject the null. We don't have any other reason to think that I should not do the test. Everything else looks to be pretty good. And so the test should be done. All the assumptions and conditions are all fine. And we don't ever use the word proof. So that's a first clue that I shouldn't be using this one or that one. The test does not give sufficient evidence. No. The test gives sufficient evidence to reject the geneticist's claim. Okay? Oh, wait. I got that backwards. Let me back up a minute. The test does not give sufficient evidence to reject the claim. So we would definitely fail to reject the null, right? So C is the one that we would go with, right? Does not give sufficient evidence would be not enough evidence to reject, and we would definitely fail to reject the null in this case. Okay, number 2. Two-way table here. So I'm down to using the chi-square test. That's the one in the calculator. It says, is there enough evidence between catching a cold and taking vitamin C? And so we're going to go into our matrix, second matrix, go over to edit, and I'm going to use this is a 2 by 3. It's 57, 26, 17, 223, 84, and 43. This goes in my, that's matrix A. I'm going to go to chi-squared test, and that's all the way down. observed and expected. All that good stuff's good to go. I'm going to end up with a p-value of 0.37. Here again, I don't have enough evidence to say the relationship exists, right? So we would fail to reject the null. So we're basically saying that they are, let's see, where's the relationship? The determinism, the effective value, blah, 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 blah. Is there an evidence of a relationship, right? So this is an independence test. INDP. So my null is that they're independent, and that's what I'm going to kind of go with. The data prove, no, I don't like that. There is significant evidence at the 1% level, well, no. There is not sufficient evidence at the 10% level, definitely not. Okay? And so we don't have enough evidence here to say that it exists. Okay? Okay, number 3 is different. Okay? Now this is going to go along with, okay, we're just going to stick here for a minute. On question 3, it gives you counts instead of giving you all the different values. It gives you so many out of so many. So it's giving you the totals, and it doesn't give you a two-way table. There's 2 ways to look at this question. First of all, in your book, if you read it, which I suggest more so than ever, you should have read chapter 26. In this example, it's talking about Larry Bird hit a second free throw 48 out of 53 turns after the first one was missed, and he hit a second free throw in 251 out of 285 turns after the first three was made. Right? So it's whether he missed the first one or made the first one, and then what he either made it or he missed it on his second try. This is a bit confusing. If you have a test of homogeneity and you have a 2x2 matrix, there's just 2 variables and they each have 2 different outcomes, then you can use a chi-square test of homogeneity to answer the same question. It would give you the same results. So what I'd like to do is kind of just go to my 2-prop z-test. Just kind of follow along with me. So pause the video if you need to, and pull that up. I'm going to enter in, so we're going to let x1 be 48, and we're going to let n1 equal 53. We're going to do x2 equals 251, and n2 equals 285. 48, 53, 251, 285. Now, anytime that you do this, we're going to be using a not equal to test, right? It wanted to know, is it different? And that's a good clue there. So if I go down and I use this test, I'm going to get a p-value in this case of 0.60. So it's definitely failed to reject. There's really no evidence here that there's any difference. And so P or E would be my answer. If I wanted to do this with a chi-square test, well, it's kind of important to be able to write out your chart. Okay, so I need to create a 2-way table. So you've got your first throw, and you've got your second throw, your basket, right? So it misses it, makes it, miss, make. So this is my little 2-way table I'm going to make. And they've told me a few things, but a lot of those things aren't inside the table. They're actually totals from the table. So it says here, and I'm looking at the first set of numbers right there. It says he hit a second free throw, so he made a second one after the first, in 48 out of 53, if I can read, after the attempts, after the free throw was missed. So the first one was missed. Let me readjust that down here. So, miss. So if he attempted and he missed it a total of 53 times, and Larry Bird hit a second free throw. So his second one he made. So this is going to be 48 here. In the second number, it says that he hit a second free throw if after the first throw was made, right? So if he made the first one, and this one's going to be out of 285 times, and then he would he hit a second free throw 251 times. Now, creating this table, here again, I would recommend doing this on a 2-prop Z, because this table is a little tricky to make, especially this particular one. They're not super clear about it. So I'm going to use what I have in the table to be able to go backwards and subtract and fill in some of these things. I can go ahead and fill in these 2 blocks here, and giving me this information is enough to fill in the whole table. So I'm going to do that real quick. 53 plus 285. So there's, it's 338 here. 48 plus 251 is 299 there. Now I'm going to do some subtraction. 53 minus 48 to give me this value, so 5. And 285 minus 251, this would give me 34 here. So 39 would be there. And just to double check, 39 plus 299 gives me 338 as total. And if I come back in and I really want to do this with a matrix, I can go into matrix A. It's a 2 by 2 matrix. I'm going to go ahead and enter those values, 5, 48, 34, and 251. And that gives me my matrix A. The next thing I'm going to do is go over to my chi-square test and enter those values. And I'm going to get a p-value that's exactly the same as it was before, 0.60, 60150, whatever. They may not be perfectly the same p-value, but you're going to get pretty much, so it may be the same. I can't remember if it's exact or not. So there's 2 ways to do to the same question. Okay. This one's actually really easy. Remember, it's rows minus 1 times columns minus 1 for degree of freedom, right? What would appropriate procedure? It's asking if a relationship exists, so you're already talking about independence. Goodness if it is out of the question because it's a 2A table, so there's no way to do it. A 2-sample proportion test, that can't be done either. You have too many options. It can only be done with a 2-prop Z can be done if it's a 2 by 2. Here you've got a 2 by 3, so not a possibility. So it's an independence test. That's clear. What's my degree of freedom? It's going to be rows minus 1, so that's going to be 2 minus 1 times 3 minus 1. So that's 1 times 2 or just 2. So it tells us that C is the correct answer. Okay, there's the first page. On to the second page. In this example, number 5, it says from the data from number 4, what was the expected number of hot dog purchases? If we go back and look at that, what I'm going to have to do here, I took a quick picture of this so we can bring it to the other page. For some reason you did the test, you could go look at your matrix B. But it's asking me for the expected for a hot dog at basketball, right? So I'm looking to find this expected cell, right? So let's add up the column. That's going to be 290. If I add up the rows, that's 110 plus 240, so 350. I'm going to have to add up again. I need to somehow get the entire table's total. So I'm going to add up this next row. So 50 plus 10 is 60, or it's 150. So we have a total of 500 games. It might have said that in the previous question. I don't remember. But in order to do this, I could have used the calculator, done the chi-square test, and then went back and looked at the cell, and it would have told me. So it doesn't really matter how you want to do it. 350 times 290 divided by 500. 350 times 290 divided by 500. And we get, never mind. Oh, okay. It helps if you type it in right. Try that again. 150 times 290 divided by 500. I want to say the answer is like 87 or 83.3. I can't remember. Yeah, it's D. So you're going to get 87 is your answer. Remember, perfect independence says I want a chi-squared statistic of 0. They're perfectly proportional. And the way we can do that really easily is n over 35 is equal to 52 over 10. And obviously, I have to multiply. I can cross multiply, but really I'm going to do is going to be 35 times 52 over 10, and that's going to tell me what my n value is. So 35 times 12, no, 52 divided by 10 is 182. Okay. It is generally argued that the chi-square distribution is appropriate when we have an expected cell count that's at least 5. So let's find out. Samples at least 30. Nope, that's nearly normal for the t-test. Observed cell counts. No. Sample size is large enough so that all the expected counts are at least 5. Yep, that's the one. Sample size is large enough for at least 1. No. Sample size is large enough so the no. So yeah, definitely C. Okay, 8. This one's tricky. This one has a slight problem. You're missing values here, and it looks like the first two are the same answer, but they only look the same because the numbers that are missing. So we're going to kind of approach this one in more of a FRQ type situation. We can narrow our answer choice down to one of two answers, but no further. So this one definitely helps to make a two-way table with it, right? So we're going to talk about we're going to set this is heart attacks, and this is going to be baldness. And so this is yes and no, yes and no. So what we're going to have here is the little two-way table. And this is a lot like what we did before. It's going to allow us to get all of our totals down, and we can use the chi-square test to do this as well. Okay, it says that 665 patients are admitted with heart attacks, right? So heart attacks, yes. So this is going to be 665. And 214 of those had baldness. Okay, while the 772 non-heart, right? So 772 here, and that 175 had baldness. 175. Is it evidence at the 5% alpha level that there exists a relationship? We're using a chi-squared test for independence. Let's go ahead and fill in the rest of this chart. So 665 minus 214. This is going to leave me with 451. 772 minus 175 is going to be 597. Now, I don't need the totals here. I just needed to get those numbers inside the table. So at this point, I'm going to go to my chi-square test. And I'm going to enter the data in the matrix. So 214, 451, 175, and then 597. Double check, make sure you don't make any mistakes. Then we can do the test. Okay, so it looks like we got a chi-squared value of 16.4 and a p-value that's roughly 0. Okay, it's got 4 decimal places. 0.000052 is technically what it is. But I just needed to know, is there a relationship, right? And so I'm going to reject my null. Remember, the null for tests for independence is that they are independent. There exists no relationship. So when I reject that null, I'm deciding that there is, in fact, a relationship between the two variables. Okay, so is it sufficient evidence at the 5% significance level to say there's a relationship? Yes, I'm rejecting the null and concluding there does exist a relationship. And the question would be, if I'm looking at a chi-squared test, okay, there exists some number for chi-square here that marks off where 5% starts. So I got a chi-squared statistic of 16.4. At some point in time, my chi-squared value got to be a certain value, and any value higher than that would get me to reject the null. I'd like to know what the critical chi-squared number is that starts at 5%. Okay, grab your formula sheets, okay, and pull those in and look it up. I'm going to see if I can pull up a copy of ours. Let's see. So while I'm doing this, you grab your chi-squared statistic, your chart, and we'll compare notes. If you've got your formula sheet, you can do that. If you want to pull up your book, it's actually in your books as well. Okay, so at this point, we have, if you think about it, how many degrees of freedom do we have? Well, we've got 1. It's going to be 2 minus 1 times 2 minus 1, because that's the rows minus 1 times columns minus 1. This is going to be a degree of freedom of 1. And so what I'm going to do, I'm going to look at my table. This is the chi-squared table, right? So make sure that you have the right table values. I'm looking for this number here that matches up with my alpha level. Well, your alpha levels are at the top, and then your degree of freedom is on the side here. I want to figure out what's 1 degree of freedom. I'm going to go over to 5%. The critical value that I need to reject is 3.8. So if I had gotten a chi-squared statistic of 3.84, or anything bigger than that, I would end up rejecting the null, right? So as they get larger, you see the probability goes way down. So the answer would have been A or B. We don't really know which one it is because the critical elements that distinguish those two things apart are lost. But that's how I use my table in my chi-squared values. Okay, let's get rid of that. Let's move on. Okay, number 9, this one's really easy. Remember, this is about 10 intervals, right? You're looking at, this would have been a goodness of fit test because you have 10 class intervals to do the statistics. And it's not about the N observations, it's about the actual categories. And so this is a N-1 type of degree of freedom. Okay, it had to have a two-way table in order for it to be like N-1 or rows -1 times columns -1, but I didn't even have that option here. Like I can't even do that. And so we know it's going to be 9 degrees of freedom because you're going to have 10 -1. Don't be suckered into thinking it's 100 -1. In chi-squared, it's almost never the sample size -1. That's always like your t-test. Okay, now down to number 10. The chi-squared inference procedures deal with categorical variables. Absolutely 100% true. The chi-square distribution is symmetric. False. Absolutely not true. We define this one as a skewed right distribution. In fact, the picture you just saw on the chart, it was a skewed right distribution. A chi-squared test of independence on a 2x2 table produces the same results as a two-tailed difference of proportions. Remember, that's a 2-prop z-test. And we've actually talked about that even just in this video. But there's a problem with this one. This one's actually false because it's not that. Okay, independence tests to see if there's a relationship. When in 2-prop z-test, we're looking to see if there's a difference in the two. So it's actually the homogeneity test. Okay, and so it's actually false, right? So actually the only one is true is number 1, and that's A. Okay, so that was the multiple choice questions. We're going to do this video in 2 parts. Okay, hopefully this was good for you. Okay, hopefully that helped to clear up a lot of things about the chi-squared statistic. Take care, and if you got questions, let me know at that point.